So let us start with Boolean algebra. And this is chapter number 2, Boolean algebra, lecture number 1. Okay. We'll start with the postulates, then few Boolean algebra identities, then few theorems in Boolean algebra. Right. Okay. After that, we'll move on to min and max terms. Right. How to represent a Boolean function using min and max terms. Okay, then we'll get into logic gates, right? Properties of different logic gates. Okay, so let us start with the postulates in Boolean algebra, right? So the Boolean algebra implies the algebra of Boolean variables. Okay, and the properties of a Boolean variable is nothing but the variable can take two values. Okay, two values. Which are those two values? 0 and a1, right? So Boolean algebra is the algebra based on Boolean variables, and those Boolean variables can take two values, either 0 or a1, right? If let us define a Boolean variable as x, right? X is a Boolean variable, right? X is a Boolean variable, right? That implies x can take two values, either x will be equal to 0 or x will be equal to 1. No other possibilities, right? So a Boolean variable implies it's nothing but a variable, but that variable can take or accept two values, namely 0 and a 1, logic 0 and logic 1, right? Similarly, if we are defining a Boolean function, that also implies that function can take only two values, right? That is logic 0 or logic 1, right? So we are having some postulates in Boolean algebra, few identities, then theorems in Boolean algebra. Okay, right. So let us get into postulates in Boolean algebra. Okay, postulates in Boolean algebra, right? And these are very simple. Everyone knows this. Postulates in Boolean algebra. That is nothing but 1 and with 1 equal to 1 itself, right? We are having two operators, basically two operators in Boolean algebra. That is a dot operator that corresponding to AND operation. An OR operator simple is corresponding to addition in decimal. OR operator, right? So if you are taking AND operation between two logic ones, 1.1, you will get a logic 1 again. If you are taking the product between 1 and 0, right? One variable is logic 0, then you're taking the product. That implies you will get a logic 0. 1.0 will be 0. Right? Similarly, 0.1 will be again 0. 0.0 will be again 0. Right? Right. If we are replacing the AND sign with OR sign, we'll get another postulates, right? 1 instead of AND, I'm using OR simple. This was AND. That's equal to 1. Or between 1 and 1 will be equal to 1. Then second case, 1 or with 0 will give me 1, right? Then 0 or with 1 again will give me 1, right? 0 or with 0 will give me 0, right? Everyone knows this. Simple postulates in Boolean algebra, right? The product operation will give 1 at right hand side RHS if and only if both are logic 1, right? The other way, the OR operation will give you logic 0, right, at right hand side. if and only if both are zeros, right? So 0 or with 0 will be equal to 0, right? These are the simple postulates. Everyone knows this. Okay. Then we'll slightly move into theorems in Boolean algebra, right? Theorems in Boolean algebra. And the most important theorem in Boolean algebra is duality theorem or duality principle, right? Duality theorem or duality principle. Duality theorem or duality principle. And the theorem is very simple, right? Duality theorem or duality principle, right? It's very simple theorem, right? Suppose we are having a Boolean function, right? Boolean function that has its own variables, let us say x, y, z, etc. Right? Right. We are going to have a function, Boolean function. Of course, the function will have its own arguments. X, y, z, etc. are the arguments, right? Here, x, y, z, etc. are called Boolean variables, right? Boolean variables, right? Boolean variables will give me Boolean function, okay? And in my Boolean function, there will be an operator, let us say OR operator will be there, right? Not only OR, it may contain AND operator also, okay? OR and AND are Boolean operators, OR and AND operators, right? Then it may contain constants, right? Constant symbolize logic 0 and logic 1, okay? So I have a Boolean function that consists of variables, let us say x, y, z, etc., and number of variables, then OR operators, AND operators, constants 0 and 1, right? So if you are asked to identify the dual of the given function, right? Dual of the given function, let us say fd, dual of the given function, fd, right? Then you can easily identify the dual expression of the function f, right? That d index is called dual, right? Dual of the function f. Function f is given to you. You are trying to get the dual expression of the function f. That is denoted by fd. Okay. So while evaluating the dual expression of a given expression, right? Please listen carefully. The variables are not changed, right? You should keep the same variables in the same form. X appears as x, y appears as y, z appears as z, etc., etc. Not change in variables or the forms of the variable, right? You need not write x with x complement or y with y complement, nothing else. And you should repeat x as x itself, y as y, etc., z as z, right? Then, if you're observing an or sign in your expression, you are trying to evaluate the dual expression of the given expression ft, then you should replace the or sign with the and sign, okay? Right? If an expression is given to you, if you're asked to identify the dual expression, then you should not change the variable or form of the variable. Keep variable as such. Then if you're observing an or sign, you should replace it with and sign. Similarly, if you're observing an and sign, you should replace that with or sign. Okay. So you should convert or to and to or. Right. No changes for variables. Right. Right. So in your expression, if you're observing a constant, let us say logic 0, if you're observing a logic 0, then you should replace that 0 with its complement. Complement of a 0 is 1. Okay. Similarly, if you're observing a 1 in the initial function, right, while evaluating its dual function, you should replace that logic 1 with its complement, that is logic 0. So the duality theorem is very simple, right? If you're having an expression, given expression, then if you're asked to identify the dual of the given expression, then you should keep the same variables, same forms, right? If you're having and sign, replace with or sign. If you're having or sign, replace it with and sign. Logic zeros to logic ones and logic one with logic zeros, right? Let's take an example. If you're having, let us say, x or y equal to 1, right? X or y equal to 1 is a given expression, right? If you're asked to identify the dual of the given expression fd, then as we discussed, no change for x as such. This or sign will be replaced with the and sign. No change for y, okay? Right hand side, equality, no change. Right hand side, we are having a logic 1 here, right? That one should be replaced with a logic 0, right? So the second expression is the dual expression of first given expression, right? Let us take another example. If x bar plus x equal to 1, if you asked to identify the dual expression of this, then x bar will appear as such, no change. This is an or sign that should be replaced with and sign. No change for x, no change for equality sign. Right hand side, you're having a logic 1, you should replace it with a logic 0, correct? So that is nothing but duality theorem or duality principle, right? And we have one important statement in connection with the duality theorem. And that is important. Okay. Duality theorem is very simple. And the statement in connection with duality principle is also important. Right. So please write down the statement. Statement is also very simple. It says that if a Boolean expression is is valid is valid if a Boolean expression is valid, then then its dual expression is also valid. Dual expression is also valid. Okay, is also valid. Okay, that is, if a given expression is valid, then its dual form also will be valid, right? Okay, is that clear? Duality principle, how to take a dual expression of a given expression, and the statement, if a Boolean expression is valid, then its dual expression is also valid. We'll have a few examples to illustrate the last statement. Okay, is it clear up to this first slide? Please respond through the chat box. Please respond. Is it clear? Duality theorem or duality principle? Right. Only if you are responding. Others, if you have any issues, you please type it in the chat box. Otherwise, you please respond that everything is fine. Okay. Is it clear? Please respond yes or no. Clear? Shall I proceed? Right. There is no face-to-face contact, so I cannot collect the feedback. Right. The only option is through the chat box. Right. So please put your feedback in the chat box. Okay. Right. So let us move on to next slide. We'll elaborate the statement. If a Boolean expression is valid, then its dual expression is also valid, right? So let us have one Boolean expression, right? Simple Boolean expression, that is, everybody knows this, 0 dot x. What will be the answer? 0 dot x. The result will be nothing but 0 itself, right? Okay. So this is a valid expression. What is the dual of this? This is true. This is a valid expression. What is the dual expression of this? While taking the dual, 0 will become logic 1. Okay. And sign will become or sign. no change for variables. So x will remain as x itself, no change for equality. Right hand side I am having a 0, that should be replaced with a 1, right? So this is another theorem. 0 dot x will be 0 always, and 1 or with x will be 1 always, right? So the second form is actually dual of the first given expression. So this is the dual form. Okay, this is given expression. Okay, so what we said in the last slide, that if a Boolean expression is valid, then its dual expression is also valid, right? So we took an expression, valid expression, and we understood that the other expression, that is 1 or x, 1 plus x, will be 1 itself, right? So if you are adding a logic 1 with any variable, right, 1 plus any Boolean variable, the result will be 1 itself, right? 1 itself, right? So similarly, another simple expression is 1 dot with x will be equal to what? X itself, right? X itself. What is the dual of the given expression? Dual expression will be 1 or with, okay, or with no change in variables. So x equal to right hand side x itself, right? Right. Sorry, I should take the dual expression. So while taking the dual of logic 1, I should write logic 0, right? So logic 1 should be replaced with logic 0, and sign should be replaced with or sign. So 0 or x equal to right hand side the variable. So no change in variable. So 0 or with x will be x itself. So if 0 is added with any Boolean variable, the result will be the same Boolean variable, right? Right, correct. Then another simple form of Boolean expression is nothing but, let us say, x dot with x dot with etc. etc. Continuous product of the variable x. What will be the result? If you are taking the product with the same variable, that same variable can take two values, either logic 0, if x equal to logic 0, then the product will be equal to 0. If x equal to 1, then the product will be equal to 1. So the product will be same as same variable, right? X, right? So x dot x will be, etc. will be same as x. And the dual expression of that will be x and sign with or sign, right? And sign with or sign, right? Not change for variable x plus etc. Right hand side is equal to no change for equality sign. What is your right hand side? X, no change for x, because I'm taking the dual, right? So x or with x or with x is equal to x itself, right? So if you're adding the same variable n times, the result will be the variable itself. Similarly, if you're taking the product of n variables, same variable n times x dot etc etc, the result will be x itself, right? And this particular law is called identity law, right? Identity law, okay? Identity law or idempotent law, right? Idempotent law, idempotent law, identity law or idempotent law, right? Right. Again, we are having another identities. Let us say the OR operation between the variable and its own complement, x plus x complement, right? So x can take two values. If x equal to 0, what is complement of x? Will be equal to 1. So that result will be equal to 1. Okay, 0 or with 1 will be 1. If that x equal to 1, its complement will be 1, complement will be 0. Okay, 1 or 0 again equal to 1. So irrespective of the value of x, x can be either 0 or 1, doesn't matter, right? This expression will be always equal to how much? How much? Always equal to 1, right? So x plus x complement will be always equal to 1, right? And similar to this, if you're taking the dual expression of x plus x bar equal to 1, right? Dual of x is x itself, or sign should be replaced with an sign, right? X bar will be x bar itself, not change. I'm taking the dual expression. Equality, same sign. Right hand side, I have 1. Right? If you're taking dual of logic 1, you should replace that 1 with a logic 0, as we discussed. Okay, so this will be 0. Right? So this is valid. Its dual expression also valid. Right? So these are the identities in Boolean algebra. Right? Right? You can expect a one-word question based on this. Which one of the following is true? X dot x complement equal to, four options will be there. X dot x complement will be equal to 0, 1, x complement. X dot x complement. X dot x complement will be always equal to 1. Right? Okay. So these are simple identities of Boolean algebra. Right? Boolean algebra is nothing but algebra of Boolean variables. The speciality of Boolean variables are those variables can take two values, either logic 0 or logic 1. And the operation, basic operations are OR operation, AND operation, and complement operation. Okay, right. Then we'll get into commutative law and associative law. Okay. Up to this, it is clear. X dot x complement 0, x plus x bar equal to 1. Is that clear? Please respond. Yes or no? Okay, right. Then we are moving to another law, that is commutative law. That is also very simple. Commutative law, right? Commutative law, right? Commutative law. And that is very simple. If you are taking the OR operation between two binary variables, let us say x and y, right? If you are taking OR operation between two binary variables, x and y, right? If you are interchanging the order, in place of x, you are taking y, then OR with, instead of y, you are writing x, right? If this is true, then we'll say that the OR operation, which operation it is? OR operation is OR, right? OR operation is commutative. Okay, OR operation is commutative. Okay, if you're taking the dual expression of this, what is the dual expression of this? Dual expression will be x or with y, right? X or with y should be replaced with x and with y. Right hand side, equality no change. No change for y, or sign should be replaced with the and sign by x. So this is the operator is called nothing but AND operator, right? So both the OR and operators are commutative, right? Both OR and operators are commutative. Okay, commutative. Basically, all common logic gates are commutative, right? A and B same as B and A or B is same as B or A, right? NOR operation is also commutative. NAND operation is also commutative. XOR operation is also commutative. XNOR operation is also commutative, right? All basic gate operations are commutative, right? Clear? Then let us move to associative law. What is associative law? Right? Associative law, right? That is also very simple. Instead of two variables, we are having, let us say, three variables. Okay, let us say x, y, and z. Okay, so I'm taking the OR operation between the OR operation of y and z. Okay, y or z, right? I'm taking the OR operation between y and z first, then I'm taking OR with x, right? And that is same as first taking the or with x and y, then or with z. So if this is satisfied, then we'll say that the associative property is satisfied, right? Similarly, if you are taking the dual of this, right, dual of this x and with y and z will be same as x and y first, okay, dual of this x and y and with z, right? So it's a case with the three input variables x, y, and z, right? Right. So I'm taking the variable x, right? I'm taking or between y and z. Okay. This is my or gate. Logic gates will study in detail, right? So that is same as this connection is same as taking x and y or operation first, x or y, then followed by z, right? Right. So three input or operation and three input and operations are commutative, right? But you should remember here, three input NAND and NOR operators are not associative, okay? Not associative, okay? You should remember this. NAND and NOR operations are not associative, okay? You can expect a question based on that. Which of the following is not associative, right? NOR and NAND operations are not associative. That you can keep in your mind. Okay. NOR and NAND operations are not associative, right? All other operators are associative. Okay, right? Is that clear? Shall I move to next slide? We are having a distributive law, then absorption law, and then we'll get into a few more theorems. Then simplification of Boolean algebra. Is that clear up to this? Please respond yes or no. Students, please respond. Only if you are responding. Lolita, Shalindra Singh. What about others? Please respond. Right. Shall I move to next slide? Copied. Done. Okay, right. I'm moving to next law, that is a distributive law. Right. Distributive law. Right. Distributive law. That is also very simple. Distributive law. Right. Distributive law. That implies x plus y z can be expanded or elaborated as x plus y dot z can be expanded as x plus y, right, dot with x plus z, right, x plus y dot x plus z. We'll say that here the operator is or, okay, this is or operator, okay. So that or operator is getting distributed, okay. Two or operators are here, right, distributed, right, over which operation? Over and operation, correct, right, and this is and operation, right. Or operation is getting distributed over and operation. Then we will say that and sorry, or operation, or is distributive, distributive over, over which operation? Over and operation, right? And operation, right? So x plus y z can be expanded as x plus y dot x plus z, or the other way, the expression x plus y dot x plus z can be simplified into x plus yz, right? Both ways it is correct. The expression x plus y dot x plus z can be simplified into x plus yz, or the other way, the expression x plus yz can be expanded as x plus y dot x plus z. And then let us take the dual of both sides, LHS and RHS, right? So dual of x will be x itself, or sign will replace with and sign. Y dot z will be y or z, right? That would be same as dual of right hand side, x or y, that is x dot with y, right? This and sign should be replaced with or sign, right? X, this or should be replaced with and sign x dot z, right? So x dot y or z is same as x dot y plus x dot z, right? That is called distributive law, and the second expression is called dual form of the first expression, right? X plus y z equal to x plus y dot x plus z, right? Okay, right. Then we are having one more simple expression, right? That is called absorption law, right? Absorption law. Absorption law, right? That is also very simple. If you are taking the or between x and product of x dot y, x and y, x plus x dot y, that will be same as x is common, right? So one or with y, right? And we conclude that one or with any variable will be one itself. So this is nothing but x dot 1, right? So simply x plus x dot y is same as x itself, right? So x plus xy is same as x, right? If you're taking the dual expression, that is also valid. What is the dual of this? Dual of this, nothing but x and with x or y is same as x itself, right? So this is called absorption law. Why it is called absorption law? There was a y and that y is disappeared, right? This is equivalent to the variable x itself, right? Right. So distributive and absorption laws are important, right? Distributive was x plus yz is equal to x plus y dot with x plus z, and absorption law was x plus xy equal to x itself. Okay, that is important, right? Okay, right. Then we are having another important theorem, that is a plus a complement dot b equal to, what is a plus a bar b? A bar means the complement of variable a or with a bar and b will be equal to what? What is the simplified expression of a plus a complement b, right? If you're unable to find this, no problem. Let us take the dual expression of this. What is the dual? Dual of a is a itself. What is the dual of or sign and sign? Dual of a complement is a complement itself. Dual of and sign is nothing but or sign, correct? Right? Then if you are splitting into two, a dot with a complement or a dot b. Okay, a dot a complement, what we have concluded was a dot a complement will be always equal to 0. So 0 or with A dot B is nothing but A dot B itself, right? So the simplified expression corresponding to A or A bar dot B was unknown, but I took the dual expression of left hand side. This is my left hand side, and left hand side simplifies to A dot B, right? Right. Dual expression of A dot B will be nothing but A or B, right? So I took the dual of left hand side, then I simplified, then again I took the dual expression of that simplified expression. Then I will get the simplified expression corresponding to the original expression, right? That is application of duality theorem. So A plus A bar B is nothing but A plus B, right? A plus B. Okay, and that can be verified using truth table also, right? We are having two variables, right? Right. So if you're having two variables, how many combinations are possible? Let us take single variable, then we'll get into two variables. Suppose if x is my variable, x, how many combinations are possible? X can have a value 0 or a 1, right? If I am having a and b, two variables, right? If a equal to 0, b can take either 0 or a 1 with a equal to 0, right? If a equal to 1, similarly, b can take two values, either 0 or 1 with a equal to 1. So four combinations are possible, right? Four combinations are possible. So if we are dealing with one variable, total number of combinations will be 2 power number of variables. Okay. If number of variables equal to 1, we'll have two combinations, 2 power 1. If number of variables increased to 2, we'll have 2 power 2, 4 variables. If we are dealing with three variables, let us say x, y, and z, so 2 power 3, we'll have a total of 8 combinations, right? So in this example, we are having a and b, 4 combinations, right? So if I'm writing a plus a complement b, right? Right. A equal to 0 or with a complement is 1 because a equal to 0. I'm trying to fill a plus a bar b column, and dot with what is b? B equal to 0. So a plus a bar b, if a and b are equal to zeros, a bar b will be a plus a bar b will be equal to 0. Second case, if a equal to 0, b equal to 1, a is 0, so 0 or with 0 complement, that will be 1, dot with what is b? B equal to 1. So 0 complement will be 1, 1 dot 1 will be equal to 1. So second entry will be 1, right? Similarly, third entry, a plus a bar b, a is nothing but 1. So 1 plus any quantity will be equal to 1. So third entry will be 1. Fourth entry anyway, both a and b are 1. So this will be 1. And if you are observing that it is same as a plus a bar b is same as the OR operation between a and b, 0 or with 0, 0, 0 or with 1, 1, 1 or with 0, 1, 1 or with 1, 1. So that is same as a or b. So this you should keep in your mind always, right? This, based on this, you will have questions in the examination. So a plus a complement b is equal to a or b, right? A plus a bar b equal to a plus b, and you can verify that either taking the dual expression like this or using the truth table, right? Both columns are same. That implies a plus a bar b equal to a or b, correct? That is important. A plus a bar b equal to a or b, right? Okay. A plus a bar b equal to a or b, right? Okay. We'll have few questions based on this, what we have learned so far. Then we'll move on to next topic. Okay. Shall I move to questions? Please respond. Is that clear up to this? We have learned duality theorem or duality principle, then few postulates and few theorems in Boolean algebra. And distributive law and the expression a plus a bar b equal to a plus b, both are important, right? A plus a bar b equal to a plus b, a plus b dot, a plus c equal to a plus bc, right? A plus bc, right? This one, a plus b dot a plus c equal to same variable a plus product between b and c, right? Same variable x, or with the product between y and z, right? So a plus b dot with a plus c is same as a plus bc, right? And the last expression, a plus a bar b equal to a plus b, right? Shall I move to questions? Is that clear? Shall I move to question number 1? Right? Shall I move? Right? Okay, simplify the given expression. Simplify the given expression. Simplify the given expression. X plus p dot with x plus q. Simplify the given expression. X plus p dot with x plus q. You will be having 4 different options. Let us say x. First option is x, then x plus p, x plus q, then x plus pq. Simplify the expression x plus p dot x plus q, right? What is the answer option? Which option is true? This is of the form a plus b, okay, dot with a plus c, and that is nothing but a plus b dot c. A is nothing but x, b is p, c is q, so x plus p dot q, right? Okay, very good. If the question is slightly modified as, let us say, x plus p dot with x plus q dot with x plus p complement, what will be your answer? Again, you'll have same options a, b, c, and d. X, x plus p, x plus q, x plus pq. Right? What is answer? Look at the expression x plus p dot x plus q. This is of the form a plus b dot a plus c. This is a plus bc. That is a plus x plus pq. Okay, this one. And the remaining term is dot with x plus p complement. Again, this is of the form a plus b. This entire term is b dot with a plus c. That is nothing but a plus b dot c. Okay. So what is a here? X, right? X. What is b? B is nothing but p dot q. Okay. What is c? C is nothing but p complement, right? So we are having a p here, p complement here. What will be the product? 0. Okay. So x plus 0. What is x plus 0? X itself. Correct. So first option is the right choice. Right. So please remember that a plus b dot a plus c is same as a plus bc. Product between other two variables p and q. So x plus pq. Clear? Is that correct? Right. Only Few are responded. What about others? Is that clear? You can expect a question based on this, right? Okay, so if you're having P and P bar, thus the result, the product will be 0 always. Okay, correct. Okay, clear? Shall I move to next topic? Next theorem. We have learned only one theorem, that is duality theorem or duality principle, and few small theorems, right? We are moving to the second important theorem, that is called De Morgan's theorem. Shall I move to De Morgan's theorem or De Morgan's law? Then copied? Yes. Okay. De Morgan's law or De Morgan's theorem. De Morgan's law or De Morgan's theorem. And that is also a very simple theorem, right? It has two statements. Statement number one, that is very simple. It states that, right, complement of a sum, complement of a sum is equal to, right, complement of a sum is equal to product of their individual complements. Individual complements are A complement, B complement, C complement, etc. So A plus B plus C, etc., etc., the whole complement is equal to A bar dot B bar dot C bar, etc. So the first statement states that the complement of a product is equal to, sorry, complement of a sum is equal to product of their individual complements. Okay, these are individual complements. Complement of a sum is equal to product of their individual complements, right? Then statement number two, similar to this statement number two. Actually, it's a dual of first statement. Okay, what is the dual of first statement? A same as A, or with and, B as B, or with and, C and, etc. And I should not change the complement while taking the dual. Okay, so this is the dual of statement number one. Right hand side also I should take the dual. A complement will be A complement in dual form. Okay, no change for variable or variable form of variables. A bar should appear as A bar itself while taking the dual, right? But this and sign should be replaced with the or sign, right? B bar as such and with or, C bar as such and with or, etc. And what is the second statement? The complement of a product, okay, complement of a product is equal to sum of their individual complements, right? Complements. These are individual complements. Okay, this is very simple. De Morgan's law or De Morgan's theorem, right? De Morgan's law or De Morgan's theorem, correct? Okay, clear? De Morgan's law, very simple. Complement of a sum equal to product of individual complements. Complement of a product is equal to sum of individual complements. Right. Let us have a question based on this. Question number two. The expression A or B, the whole complement is equal to four different options. Four different options: A, B, C, D. A bar dot B bar, A dot B, A or with a complement, A bar with a B bar. The expression A plus B, the whole complement, is same as four different options. Right? Option A is the this is right. Direct question. Option A is the right choice. That was very simple. Question number three. Question number three. Right, Vilas, are you trying to say something, Vilas? Right, let us continue. The expression x plus xy, the whole complement, okay, x plus xy, the whole complement, is same as four options, four options, four options, x plus y, right, right, then logic 0, logic 1, x. What is your answer? Right, very good. Right option is option C, right? So this is x. What is x dot y, the whole complement? X bar dot y bar, right? And this is equal to logic 1. Is that correct? X plus x bar dot y bar. This is of the form, okay? This is of the form A plus a bar dot B. What is A? A is nothing but x, right? A complement is x bar and B is y complement. What is A plus A bar B? That we have learned as A or B, right? So your x plus x bar y bar will be equal to A plus B. What is A? X plus what is B? Y complement, right? And none of the option matches. So let me add as fifth option x plus y complement, right? So logic 1 is wrong, right? Correct. Answer C is wrong. So x plus x dot y, the whole complement. Apply De Morgan's law here. This will split into, sorry, this will split into x, right? Sorry, x bar plus y bar, sorry. So x plus y bar, right? And the answer what you said was correct. Sorry. So this is x bar plus y bar, and I have x plus x complement here, right? Plus x complement will be always equal to 1 plus y complement, right? 1 plus any value will give you logic 1, right? Then as you said, option C is correct. That was my mistake. So I'm eliminating option E, right? 1 is correct answer, right? X plus x bar xy, the whole complement. Xy, the whole complement, as per De Morgan's law, is the product of x bar and y bar. Sorry, the sum of x bar and y bar, right? So x plus x bar will be 1, 1 plus y bar will be always equal to 1, right? Right. And what if the question is modified slightly? Let us say x plus y, the whole complement. Then what will be your option? What is your answer? The expression x plus y, the whole complement, is same as, then this will be x plus y, the whole complement, as per De Morgan's law, product of x bar and y bar, right? This is of the form a plus a complement dot b. That is nothing but a plus b, that is x plus y bar, right? So if this is the question, then you will have right option as x plus y complement. Correct? Right? Right. Okay, so what we have learned so far is two important expressions, that is a plus b dot a plus c equal to a plus bc, and a plus a complement b is equal to a or b, right? And this will be useful while solving the questions from Boolean algebra. Okay, that you should keep in mind. And along with that, duality theorem. Okay, duality theorem and De Morgan's law. Both are simple, right? So if you are comfortable with this, we'll move on to next important topic, that is called mean and max terms. Okay, mean terms and max terms. Mean terms and max terms. Mean and max terms. Mean and max terms. This is the most important in digital electronics, right? All upcoming topics are related to the mean and max terms, right? So you should be clear with the mean and max terms for the proper understanding of the remaining upcoming topics. Okay. If you are comfortable, we'll move on to mean and max terms. Shall I continue? Important topic in digital electronics. And definitely you can expect a question from mean and max terms. Shall I proceed? Right. And I request all of your attention so that it can be easily learned in the class. Okay. Anyway, we are spending 2 hours here in the class. So let us learn in the class itself. Okay. Right. If you are not able to follow this, you please put it in the chat box. Then I will make it clear. Okay. So shall I proceed with the min and max terms? Right. Min and max terms. Important, and that is the prerequisite for logic gates. Okay. Logic gates. Shall I proceed with min and max terms? Okay. Right. Okay. So please listen carefully. Right. Let us have a system or a binary or digital circuit with two Boolean variables or binary variables, okay, as inputs. Two binary or Boolean variables, let us say X and Y are the inputs, and I have a logic circuit, okay. That logic circuit accepts two inputs, let us say X and Y, and produces its own output, Boolean function denoted by F, okay. And that F will be a function of its input. Inputs are X comma Y, right? So the arguments of the function F is nothing but the inputs. They are X and Y, right? So X and Y are binary variables. The function F is also a binary function or Boolean function, right? X, Y, and F are Boolean variables and Boolean function. X, Y are Boolean variables. F is a Boolean function, right? Boolean function implies it's an output function, and that function can take how many values? It's a Boolean function. How many values? That function can take two values, either 0 or a 1. Similarly, the input variables X and Y are also Boolean. So X and Y can take two different values, either 0 or a 1. Okay. And since I have two variables, please listen carefully, two variables, as we discussed earlier, two variables, X and Y. How many combinations are possible? I have 0, 0 combination, then 0, 1 combination, 1, 0 combination, and 1, 1 combination. These four are the possible combinations at the input side with respect to X and Y, right? Both X and Y are 0, 0, both X and Y are 1, 1, or X0, Y1, or the other case is X1, Y0. Four possible combinations. Okay. And the logic L is having some property. Okay, logic L is having some property. Its property is very simple. Its output, right? Property means the property of the output of my logic L. Okay, that logic L will produce different output corresponding to different input combinations, right? Let if x and y are zeros, my output function is 1. Okay, let us assume f equal to 1. Whereas if x equal to 0, y equal to 1, let us say my output equal to 0, right? I am taking an example, right? This is an logic. The property of the logic is that if x and y are 0, 0, immediately the output will be 1. If x equal to 0, y equal to 1, second combination, output will be 0. Right. Similarly, third combination, let us say if x equal to 1, y equal to 0, x equal to 1, y equal to 0, again the function will be equal to 1. That is a property of the function. Let us assume. And if both inputs x and y are 0, let us say the output should be 0. Output is 0 if x and y are 1, 1. Okay. That is the property of the given function. Okay, understood. Right. So this table is called truth table, TT, truth table, right? So truth table is nothing but it contains all possible combinations and the output of my circuit corresponding to particular combination, right? All four combinations are there and the output corresponding to each combination. Okay, right. Okay. So my aim is to represent the function f of x comma y using min and max terms, right? Right. A Boolean function can be represented by either using min terms only or using max terms only. Two possibilities are there, right? So let us define min and max terms corresponding to x and y combinations. Then we will see how to represent the given function having the same property illustrated here using min and max terms. Right. While representing using min and max terms, we'll have SOP and POS forms. Okay, that we'll discuss while representing the functions. Okay. So meanwhile, let us define min and max terms. Okay, so I have two variables x and y. Four combinations were possible, right? Four combinations were possible, right? So let us define first min terms. Okay, min terms, please listen carefully. Min terms are nothing but product term. Okay, product term. Okay, product term, right? Min terms are product term, and that product should return a logic 1. Clear? Logic 1. Logic 1 corresponding to each combination. So each combination will have its own min terms, right? And min terms are product terms of x and y or different forms of x and y. And that product term should return a logic 1. That is a property of min term. Okay, please understand that is a property of a min term, right? So x and y are zeros here in the first entry. And I should write a product expression, product between x and y, or x bar and y bar, or x and y bar, different combinations. But that product term should return how much? A logic 1. So if both x and y are zeros, the only possible product term that returns a logic 1 is nothing but x bar dot y bar. Correct? If x equal to y equal to zeros, the expression x bar dot y bar will be equal to 1. Correct? X is 0, x bar will be 1, y equal to 0, y bar will be 1. 1 dot 1, we know that it will be equal to 1. Right? Correct. So that is a first min term. Right? And that min term is denoted by small letter m. Okay? Small letter m min term. And it will have index. Okay? index. Index is corresponding to the decimal equivalent of that particular combination. What is the decimal equivalent of 0, 0? That is nothing but 0 itself. So that is M0, right? Please listen carefully. It will take hardly 5 or 10 minutes, but uh, it will be helpful for you all while learning the digital electronics, right? The upcoming portions, right? So the product term corresponding to x equal to y equal to 0, and that should return a 1. The expression will be x bar dot y bar, and the index corresponding to the decimal equivalent of first combination, that is 0, 0. Decimal equivalent is 0, so M0, correct? Look at second entry. Second entry, x equal to 0, y equal to 1. If x equal to 0, y equal to 1, the product term should return again a logic 1. Then I should write x complement, right? Dot with a y, correct? Because x equal to 0, x complement will be 1, y is anyway 1, so product will be 1. And that index is nothing but, index is decimal equivalent of 0, 1. What is the decimal equivalent of 0, 1? Decimal 1, correct? Similarly, third case, the product x dot y bar, correct? If x equal to 1, y equal to 0, I should write x dot y complement, so that that particular combination, that is 1, 0, will return a 1. Okay, so x dot y complement, and decimal equivalent is 2, so this is nothing but M2, correct? M2. And of course, the last combination product should be equal to 1. Both x and y are 1. So x dot y will be enough to make a product equal to 1. Both x and y are equal to 1. And the decimal equivalent is 3. So that is nothing but M3. Right. So look at the table. For a two variable system, maximum possible combinations are 4. Right. Similar to that, maximum possible number of min terms are also 4. M0, M1, M2, M3, 4 min terms, right? So if you're having two variables, 2 power 2, 4 combinations, 4 min terms. Similarly, if you're having 3 variables, 2 power 3, 8 combinations, 8 possible min terms, maximum numbers. Okay. So the property of a min term is that for that particular combination, we should make a product term, and that product term should return a logic 1 corresponding to that particular combination. Clear? And how to express the function f, we'll see later. No problem. So right now, you should understand what is the property of min terms, how many min terms are possible, how to write individual min terms corresponding to the combinations. Is that clear? Please respond so that I can move to max terms. Hold on, we will see how to express the given function using min or max terms. Don't worry. But if it is clear, I can move to max terms. Please respond only if you are responding. Chaitanya, Venkata, Gaur Kumar, Jimmy, Ravindran. What about others? Please respond so that I can comfortably move to next topic, that is max terms. Definition of max term. How many max terms are possible? How to write max terms? Okay. Then we'll express the function, this function, this one, using min terms or max terms. Then we'll have two different forms, POS and SOP. That we'll discuss. Right. So up to this is clear. Min terms are clear. Right. Shall I move to max? Okay. Right. So let us define max terms. Okay. Max terms. Max terms. Max terms. Okay. So it's a dual of actually it is not actually dual, but it's a dual form. Okay, right? So max term should evaluate to logic 0, and max terms are sum terms. Okay, right? So product will become sum, 1 will become 0. Right? Max terms are sum terms, and that sum should return how much? Logic 0. Right? Please understand. Okay. Max terms are sum terms, and that sum should result a logic 0 corresponding to what? Corresponding to individual combinations. Okay, right? So look at first entry, x equal to y equal to 0. We should write a sum term in terms of x and y, and that sum term should return a 0. How to write it? It's very simple. How to write it? is nothing but x or with y. Correct? It's a sum term. It's a sum term. And that sum will result a logic 0 corresponding to first combination 0, 0. Correct? And the max term is represented by the letter capital M with a subscript equivalent to the decimal equivalent of first combination 0, 0. What is the decimal equivalent? 0, M0. Correct? M0. Look at second case, x equal to 0, y equal to 1. I should express a sum term. That sum should return how much? 0, right? So x equal to 0. So 0 or with y is 1 here. So I should write y complement, correct? That constitutes second minterm, that is caps M1. Why it is 1? Because the decimal equivalent of this is nothing but 1, right? Look at third combination 1, 0. 1, 0. I should write it as a sum in terms of x and y. That sum should return as 0 implies I should write x complement because x equal to 1 plus y itself. 1, 0 decimal equivalent is 2. So that is nothing but M2. Right? Look at last entry. Both x and y are logic 1. I should write a sum term. That sum should return a logic 0. How to write it? I should add complement of x. One complement is 0 or with another one complement also equal to 0. And that is my caps M3. So in a system, if 4 combinations are possible, we'll have a maximum of how many minterms? 4 minterms. Maximum of mass terms also equal to same number, 4 in this case. Right? 2 power number of variables. Number of variables equal to 2. So 2 power 2 is 4. So maximum of 4 minterms and max terms are possible. Okay, using 2 number of variables. Right? Okay. Then look at my function. Okay, we are going to express the function using 2 different forms, SOP and POS. Right? So look at my function. What was the function values? F of x comma y, x comma y. Function was initially 1, 0, 1, 0. Correct? So 1, 0, 1, 0. Correct? 1, 0, 1, 0. Correct? It is important. Please listen. It hardly takes 4 or 5 minutes. Okay. So how to express my function f of x comma y using min terms first. Okay. Right. So the function f equal to 1 corresponding to a combination 0, 0. Right. 0, 0. Right. And the function also equal to 1 corresponding to another combination x equal to 1, y equal to 0. Right. So x equal to y equal to 0, function f equal to 1. Okay. And if x equal to 1, y equal to 0, x equal to 1, y equal to 0, then also function equal to 1. And the function is 0 for all other combinations. 0 for all other combinations. Okay. So how to write it logically? Right? How to write it? F of x comma y. Please listen carefully. Function equal to 1 if x equal to 0, y equal to 0. Right? So if x and y are zeros, I should get a logic 1 corresponding to function. Right? Right? That is the first case. Right? I have another case also. So or with, what's the second case? If x equal to 1, y equal to 0, right? If x equal to 1, y equal to 0, then also function is equal to 1, right? X equal to 1, y equal to 0, then also function is equal to 1. How to write it as x equal to 1 and y equal to 0. So I should take a y complement. Okay. Okay. Correct. So two cases only at which function f equal to 1. Right, those two combinations are, look at here, x bar dot y bar and x dot y bar. Okay, x bar dot y bar and x dot y bar, x bar dot y bar and x dot y bar. Look at x bar dot y bar, which minterm is corresponding to x bar dot y bar? That is nothing but m0. Correct? So I can also write it as m0 or with, what is x dot y bar? Look at this. X dot y bar is corresponding to minterm 2. Right? So or with the minterm 2. So it's a sum of minterm 0 and minterm 2. The sum is denoted by the symbol sigma, sigma, right? Sigma, sum of what? Minterm 0 and minterm 2, right? And it is not required to express m always. Instead, we will specify indexes only, okay? Because m is common, right? So sigma 0 comma 2. So f of x comma y equal to sigma 0 comma 2. So please understand that if x comma y equal to sigma 0 comma 2 implies the function f equal to 1 if x and y's are zeros, right? 0 0, function f equal to 1, right? And 2 implies the mean time corresponding to decimal 2, that is 1 0 combination, right? So the function will be equal to 1 for only these two combinations, x equal to 0, y equal to 0, and x equal to 1, y equal to 0. What about all other combinations? All other combinations, by default, function equal to what? 0, right? So using min terms, we are specifying the conditions of input or the combinations that comes at the input side, and for that combinations output f equal to 1. So min terms corresponding to f equal to 1 condition. Please remember this. Min terms are product terms. That term should return a logic 1. So min term representation corresponding to a function is nothing but those combinations at which output of that function is equal to 1. Okay. And this is actually, look at this expression. It is sum of individual product, right? It's nothing but sum of what? Sum of what? Sum of individual product. Okay, individual product. That is called SOP form. Sum of individual product. SOP form. So this is SOP form, right? And this is called simplified SOP form. That is called canonical SOP form. Okay, canonical SOP form, right? So a function is represented in SOP form using, there will be four options: max terms, min terms, none of the above, etc., etc. So if you are specifying f equal to 1 condition using min terms, then that implies those combinations corresponding to those min terms, the function f equal to 1. All other combinations, function will be equal to 0. Okay. And the same function can be represented the other way also, f of x comma y, x comma y, using max terms. Okay, using max terms. What is max term? Max term will give us a 0, right? Will give us a 0. So the function equal to 0, that conditions are expressed using max terms, right? Max terms. So what are the max terms of the given function here? Max terms implies function equal to 0, right? Function equal to 0 here, function equal to 0 here, right? So what are the max terms? Max terms are third column here. Max terms are this one and this one, right? Right. So the same function can be represented using max terms also, right? Max terms implies function equal to 0 conditions. Max terms are x plus y bar, x plus y bar, x plus y bar. Then it's a product term, right? I should take a continuous product, right? If any one combination comes, then the entire product should be equal to 0. So I should write it as a product, right? So second product is corresponding to last max term, that is x bar plus y bar, x bar plus x bar plus y bar, right? This is nothing but it will be equal to 0 if x equal to 0, y equal to 1. This will be 0 if x equal to 1, y equal to 1, correct? So its max terms are 1 and 3. Look at this, max terms are 1 and 3, right? 1 and 3, right? So these are max term 1. Okay, 0 1 is corresponding to 1, 1 1 corresponding to 3. It's a product, and the continuous product is expressed using a symbol equal to pi. Okay, pi, continuous product of what? Two max terms, they are 1 and 3, M1 and M3. And caps M is repeating here. You need not write caps M always. So instead you can write the index only, that is pi of 1 comma 3. Right, the same function f of x comma y I can express using max terms also. Indexes are 1 and 3. Look at the indexes here, 0 comma 2, right? Here it is 1 comma 3, right? They are mutually orthogonal, right? The indexes present in sigma are absent in pi, right? So the function can be expressed two different ways, either sigma of what? Sigma of, look at the function is 1 here, 0, 0, that is sigma of 0. Function is equal to 1 corresponding to 1, 0. Decimal equivalent is 2, 0, comma 2. The same function is same as pi of. How to identify pi terms? Look at the function equal to 0, right? What is a pi term? Pi of, this is 0, 1. Decimal index is 1, okay? And function equal to 0 here. What is the decimal equivalent of this? 1, 1, that is 3, pi of 3, right? And look at pi expression. This is actually what? Product of individual sum, correct? It is a product of individual sum term, right? Sum terms. So it's a POS form, right? It's a POS form, and this is called simplified POS form or canonical POS form, right? So all Boolean functions can be represented in two different ways, either using min terms or using max terms. Okay. And all min terms need not participate in the function, right? Those min terms will be there in the function corresponding to that function equal to 1, 2 min terms here. Similarly, 2 max terms here. So same function can be represented two different ways using min and max terms. Okay, is that clear? How to identify min terms of a function, how to identify max terms of a function? Is that clear? How to identify min and max terms from a given truth table? Is that clear? How to identify? Observe the truth table. If f equal to 1, that will give me the min terms. If f equal to 0, that will give me max terms. And please also note that the indexes present in the min expression is absent in the max expression because min term expression contains 0 comma 2 here. Max term should not contain both 0 and 2. Max term expression will contain the other two indexes, 1 comma 3. Okay, 1 comma 3, right? One is POS form, sigma is product of individual sum, and pi is sum of individual product, SOP form. Okay, POS is specified using min terms. SOP, sum of individual product, right? Sigma is sum, right? SOP means sum of individual product term using min terms. POS implies product of individual sum, right? Pi stands for product. So product of individual sum terms. So POS is represented using pi terms or max terms. SOP, sum of individual product, is represented by using individual product terms. They are called min terms. Okay, is that clear? Representation of a function using min and max terms. Okay, that is a basics of digital electronics, min and max terms. Please keep in mind that any Boolean function, any number of variables, doesn't matter, can be expressed two different ways, by using min terms or by using max terms. Min terms will specify those combinations at which function f equal to 1. Okay. Max terms will specify those combinations at which function output equal to 0. Right. They are orthogonal. Min indexes is absent from max indexes and vice versa. Right. Is that clear? Please respond in the chat box so that I can comfortably move to logic gates. And this is a prerequisite for understanding logic gates. Everyone Clear? Okay, I'm moving to logic gates. Before that, let us check whether all of you understood it properly. So I have a question here, and that question is corresponding to truth table of two variable system x, y, 0, 0, 0, 1, 1, 0, 1, 1, and the function f of x comma y is equal to 1, 1, 1, and a 0. Identify the min terms of function f and max terms of function f. What are the min terms? Please let me know the min terms of the function, given function in the truth table. What are the min terms? Min terms are, is it 1, 2, 3? No. Min terms corresponding to f equal to 1, correct? So 0, 1, 2, correct? 0, 1, 2. Max terms corresponding to function equal to 0 case. Only one case, function equal to 0. Decimal value of 1, 1 is 3, pi of 3, correct? Okay, right. Very good. Very simple. Okay, let me have another question to check whether you understood it properly or not. Okay. Given the function f equal to x, f equal to x, f equal to x. Identify its min terms. Min terms. And of course, it's a two variable function. To specify that, I should write arguments as x comma y. Okay, it's a two variable function. F of x comma y equal to x. Identify its min terms. Min terms. I'm asking about min terms, not max. Min terms. Min terms. It's very simple. Two variables, right? So four combinations. Okay, four combinations. What is f? F equal to x. The value of f is same as x. Okay. So 0, 0 case, what is the value of x? X equal to 0. So f is also 0. 0, 1, x is 0. F is also equal to 0 because f equal to x. Okay. Last two cases, x equal to 1. So f is same as x. So f also equal to 1. Right. So what are the min terms? Min terms corresponding to sigma. Right. That will return a logic 1. Okay. 1 for function. Min terms are, what is this? Min terms are 2 comma 3. What are the max terms? Those terms which returns a logic 0 for function. They are 0, 0, 0, 1, 0, 0. Decimal equivalent is 0. So min term, max term 0, max term 0. And the 0, 1, 0, 1 implies 1, max term 1. Correct? Very good. So you can also expect a similar question in the examination also. They will give you one expression and they will ask you to identify its min terms or max terms, and they will give you four different options. Okay. Let us have another question. I am trying to expand into three variable system. Okay. Is that clear? Up to this, it is clear. Last problem. Any queries, any doubts? Yes. So we are trying to learn an important concept in the digital electronics, min and max terms, right? And almost 90% we have learned. Rest 10% we will learn through the problems. Okay. So I'm trying to expand number of systems to three variables. Okay, three variables. Okay, so I have another function of three variables, f of, let us say, x comma y comma z. Okay, and that function expression is nothing but f of x y z equal to let us say x plus, okay, x plus y dot z, y dot z. Identify the number of min terms of the function f, terms of f. Right, you should identify the number of min terms, right, of the given function, and we are having four options. Okay, four options: a, b, c, d. Okay, right. Okay, 3, 4, 5, 6 number of min terms. Three variable system. Okay, x, y, and z. So 2 power 3 is 8 combinations, right? So you should quickly identify 8 possible combinations. They are, what are the 8 possible combinations? With x equal to 0, x equal to 0, I have 4 options for y and z, 0, 0, 0, 1, 1, 0, 1, 1, with x equal to 0, right? Same combinations for y and z with again x equal to 1, right? 0, 0, 0, 1, 1, 0, 1, 1 with x equal to 1. So 4 plus 4, 8 combinations, right? 8 combinations. Okay, right? So maximum possible minterms are 8. Similarly, maximum possible max terms are also 8, right? Right. But number of minterms and max terms will depend on the function, correct? And the function has two terms, x and y dot z. Vetrivel is saying that the sound is not proper. What about others? Am I audible? Please respond, others. Right. So, Vetrivel, please increase your speaker volume. Okay. Right. I think everything is fine here in my side. Okay. Right. Thank you all. Thank you. Thank you very much. Right. Okay. Right. Okay. So f of x comma y comma z equal to x plus y z. Okay. Look at the expression. I have two terms. First term is nothing but x. Okay. X here. Okay. X here. So if x equal to 1, if x equal to 1, right, doesn't matter what will be the values of y and z. 1 plus a quantity will be always equal to 1, right? So the function will be equal to 1 if x equal to 1, correct? So if I'm writing my function here, f here, okay, right? Function will be equal to 1 if x equal to 1, right? Correct? No doubt at all, because x plus a quantity. So if x equal to 1, x equal to 1, definitely my function is also equal to 1, correct? Correct? Correct. Then another possibility is the product y dot z should be equal to 1. And the requirement is that what is the condition for the product yz to be equal to 1? Both y should be equal to 1 as well as z also should be equal to 1. Correct? So 1 1 condition comes here. Look at yz term. 1 1 condition comes here. Right? So either x equal to 1 or y and z simultaneously equal to 1 will give me function f equal to 1. Correct? So I can write a 1 here also. All other cases, my function will be equal to 0. Correct? Function will be equal to 0, 0, 0, 0. Okay. So you are asked to identify, listen carefully, number of mean terms. Number of mean terms means how many number of mean terms, right? So each one will constitute each mean term. So 1, 2, 3, 4, 5, right? So your answer is correct. 5 number of mean terms. What are those mean terms? Sigma of, what are the mean terms? Decimal equivalent of 0, 1, 1. How much it is? 3, correct? A decimal equivalent of 100. How much it is? 100 is nothing but 4 decimal, correct? 4. 101. What is the decimal equivalent? 4 plus 1, 5. Correct? 110. How much it is? 4 plus 2, 6. This is 4. 10 is 2. 4 plus 2, 6. Correct? Triple one. What about triple one? All are 1. So 4 plus 2 plus 1. 6 plus 1, 7. Correct? So 1, 2, 3, 5. 1, 2, 3, 4, 5 mean terms. Right? What are the max terms of this? That is also very simple. Max terms. You need not look at function again. Those indexes which are absent in sigma, you can directly write it as 0, 1, and 2. Right? Those indexes absent in sigma terms will give me my max terms. Okay, pi of 0, 1, 2. So number of max terms 3, 0, 1, 2. Number of min terms 5, 3, 4, 5, 6, 7. Right? Right? Very good. I think the concept of min and max terms and representation of the function is clear to all of you who listened in the class. Clear? Please respond so that I can move to logic gates. Okay, so that we will have another 15 minutes. So that will be enough to complete the first level of class in logic gates. Okay, clear? Please respond. Then I will move to logic gates. Only few students are responding. What about others? If it is clear, please respond so that I can move to next topic comfortably. Okay, so I'm moving to logic gates. Okay, logic gates. Logic gates. Okay, logic gates. Let us have a quick recap of basic gates, what you have learned in your olden days. Okay, let us take a first one as my basic gate called OR gate. Okay, please recall the logic simple of OR gate is like this. Okay, please recall this. Okay, two input OR gate, right? X and Y are the inputs. Okay, so or let me write A and B as inputs. A, B. Output Y is the sum of A and B. A or B. Sum of A and B. A or B. Okay. Right. And everyone knows the property of OR gate, right? Two inputs implies how many combinations? Four combinations, right? Very good. Four combinations. And the expression is A or B. Okay. A or B. Right. So 0 or 0, definitely that will be 0. Okay. 0 or 1 will be 1. 1 or 0 will be 1. 1 or 1 will be 1. So quickly tell me the min terms of my OR gate. What are the min
Sir?
terms?
Sir?
Yes.
Sir,
Right.
just can you explain it again, sir?
Sorry, disturb you. Can you please say which one? Which one? Right. Okay. Tell me which one I should
Sir,
repeat.
sir, before this topic, sir.
Logic gates.
No, sir, before this.
This
Yes, sir,
question.
this one. Yes, sir, yes, sir.
This question you are asking.
Yes, sir.
Okay. You properly listen the previous portion, that is min and max terms. That is comfortable.
Sir, not that much comfortable, sir. Just
Or
70%.
you just joined right now, or you are not in the class.
Sir, no, sir, I was not in the class, sir.
Okay, that's fine. Shall I explain this after completing the logic gates? Is
Okay,
that
sir, no,
fine? No,
okay, sir, no
you please
problem.
stay after the completion of the class. I will
Yes,
explain. No
yes, sir,
problem.
yes, sir.
Okay, thank you very much.
Okay, sir.
Right. Okay. So what are the min terms corresponding to this? Look at the two table. A or B will give me logic 1 here, here, here. This is corresponding to decimal 1. This is decimal 2, decimal 3. So this is nothing but 1, 2, 3. Very simple. What are the max terms? Pi of 0 term. Decimal equivalent is 0. So pi of 0. Correct. Very simple. Okay. Right. Okay. Let us move to the dual gate of OR. What is the dual gate of OR? Or was A or B? What is the dual expression of A or B? A or with and, correct? A and B. Y equal to A and B. What is that? Which gate it is? It is an AND gate. Okay. A, B, Y equal to A and B. Right. So dual of OR gate is nothing but AND gate. How to interpret that? A or B is OR gate. To take the dual of that expression, a variable is as such, or should be replaced with and B variable is as such, not change. So A dot B. So that is my AND gate. It's a very simple gate to protect. So for combinations for A and B, 0, 0, 0, 1, 1, 0, 1, 1, A dot B here. Okay, 0, 0 will give me 0, 0, 1 will give me 0, 1 and 0 will give me the product 0, 1, 1 only will get a 1. Okay, so what are the min terms? Only one min term, correct? Last entry 3. Okay, what are the max terms? More zeros, right? More zeros. 0, 1 and 2, correct? 0, 1 and 2, correct? Very good. Right, 1, 2, 3 is wrong, right? Min term is 3 and max terms are 0, 1 and 2. Right? Okay. Is that clear? Property of AND gate. Min terms of AND gate. How many min terms? Only one min term for AND gate. How many min terms for OR gate? Three min terms. How many max terms for AND gate? Three max terms for AND gate, right? Three max terms for AND gate. How many max terms for OR gate? Only one max term for OR gate. Clear? The expression is A dot B, min and max terms. Correct? Clear? Please respond. Right? Shall I move to next gate? Right? Okay? Clear? Just properties of logic gates. Problems we'll do it in the next class. Right? Okay? Okay, thank you. So next one is NOR gate. Okay? NOR gate. NOR gate is nothing but a NOT gate placed after the output of a OR gate. So this is nothing but NOR gate, right? This is not gate or inverter, not. This is nothing but OR. Okay. So the simplified simple of this is nothing but an OR gate like this with a bubble at the output. Okay, correct? Why? Right? Right. The relation between OR and NOR is that they are mutually complement. Okay, they are mutually complement. Right, mutually complement. What is the expression? It was A or B initially, or gate, not implies a complement, right? So complement of my A or B will give me NOR gate, right? What are the complement of this? It was 0 triple 1, that will become 1 triple 0 complement, right? 1 triple 0. Okay, complement of 0 will be 1, complement of 1 will be 0. So 1 triple 0 for NOR gates. Clear? A plus B the whole complement is the logic expression. And what are the min and max terms? That is most important. What are the min terms? Only one min term, that is 0, sigma 0. What are the max terms? More number of zeros, more max terms, 1 comma 2 comma 3. Right? And what is the property of NOR gate? NOR gate will produce a logic 1 if and only if all of its inputs are at logic 0. That clear? NOR gate will produce a logic 1 at the output side if and only if all of its inputs are at logic 0. Right? Logic 0. Right? That is the property of NOR gate. What is the property of OR gate? OR gate will produce a logic 0 at the output if and only if both all of its inputs are at logic 0. Right? OR gate will produce a logic 0 at the output if all of its inputs are at logic 0, whereas NOR gate will produce a logic 1 at the output side if and only if all of its inputs are at logic 0. Correct? Correct. Let us take the dual of this, dual expression of this. What is the dual expression of A plus B the whole complement? No change for A. OR sign should be replaced with AND sign. No change for B. No change for complement. What is this? This is nothing but NAND gate, correct? Complement of AND, right? NAND gate. What is the simple? AND followed by an inverter or NOT gate, correct? And the simplified simple is nothing but AND gate with a bubble, right? A, B, the bubble. What is the logic expression? A dot B, the whole complement, right? Two variable gate, two variable system. So again, four combinations, right? Four combinations, okay? A dot B, the whole complement, right? Just a complement of AND gate, okay? Look at AND gate, truth table. 0001 was the truth table for AND gate, correct? Then that will become 1110, 1110. right? Triple one, zero. And what is the property of NAND gate? NAND gate will produce a logic 0 at the output if all of its inputs are at logic 1. Or the other way, NAND gate will produce a logic 1 at its output if at least one of its input is at logic 0. At least one of its input is at logic 0, then output will be equal to 1. Or the other way, NAND gate will produce a logic 0 if and only if all of its inputs are at logic 1. You can expect a simple question based on this also, right? And what are the min terms? Min terms. What are the min terms of this? I think somebody have unmuted. Who is that? I'm having a noise. Binita Rajesh. Can you, right. Thank you very much. Okay. So what are the min terms of this? Min terms of my NAND gate. Min terms are, right, very good. Venkata Krishna is answering this. Min terms are sigma of 0, 1 and 2. Very good. Max term, only one max term, that is 3. Okay. Right. Done. Done. Very good. That implies you understood what is a min and max terms. Okay. Right. Very good. Okay. And we have two more gates to complete, right? That is XOR gate, XOR gate, and XNOR gate. Okay. It is slightly different than our conventional gates, right? XOR and XNOR gate. And please recall the simple as similar to OR. We're having two curved lines here. Okay. And this is corresponding to XOR y equal to, and the symbol of XOR is nothing but XOR, or will be there inside a circle. Okay. P. Okay. Inside a circle. Okay. Right. And the property of an XOR gate is very, very simple, easy to remember. Right. Four combinations. Okay. Four combinations, two variables. Okay. A XOR B, it is very, very easy to remember. Okay, how to remember this? A XOR B truth table. A XOR B. The property, please listen carefully. The property of an XOR gate is that, very, very simple. If inputs are different, inputs are different, inputs are different, output will be 1. Okay. Inputs are different. Look at this 0, 1. Inputs are different. 1, 0. Inputs are different. Right. If inputs are same, output is equal to 0. Or the other way, if both of its inputs are at same logic, either 0, 0 or 1, 1, XOR gate will produce a logic 0 at the output. If inputs are different, either 0, 1 or 1, 0, doesn't matter. If inputs are different, output will be 1. Correct? So what are the min terms of this? It is easy to identify the min terms now because truth table is available. Min terms are 1, 2. Very good. Max terms are 0, 3. Very good. Okay. Very good. Please remember the property of XOR gate. Similar input or same input is 0 output. Dissimilar input or different inputs, output is equal to 1. Right. So it senses the difference in output, input, difference in input. Inputs are different. It will give me a logic 1 at the output. And it's better to write the logic expression also. Okay. Logic expression is required. Okay. What is the logic expression of okay, project Vijay? Okay, it's a tricky question. Does it follow for 3 input, sir? No, the 3 input definition is entirely different. We cannot deduce it from 2 input case. It is entirely different. Okay, that will conclude while discussing 3 input gates. Don't worry, hold on. Okay, right. Three input case definition is a little bit different. Okay. And of course, that is a tricky question. We'll have a discussion on that. No problem. Okay. So how to write the logic expression? How to write a logic expression? Right. So look at the truth table. I am having a one here. I am having another one here. And minterm is 0, 1, 1, 0. That is 1 and 2. Right. So minterm 1 is corresponding to what is 1? 1 implies A0, B1. Correct. So it is nothing but A bar B. Correct. Minterm 1 is nothing but A0, B1 implies A bar B. And I have one more case, that is with A1 B0, that is A dot B complement, right? So this is the expression, right? This is minterm 1, right? This is minterm 2, right? 0 1 minterm 1 1 0 minterm 2, correct? That is a logic expression, A bar B plus A B bar, right? Different input conditions, two conditions, I am taking the or between that. Okay, so that is nothing but this is sigma 1, so this is nothing but sigma of 1 comma 2, right? This is sigma 1, this is sigma 2. Okay, right? Okay, right. What about x nor? What about x nor? If I'm taking the dual of this, listen carefully, dual expression of that, dual of a is nothing but a, dual of circle is same circle, but dual of or is nothing but and. Okay, and. So a dot in a circle. Dual of b is nothing but b itself. It's an x nor, or and nor. So the symbol is similar to curved lines, and I have an not gate here. Okay, a and b. So simplified simple will be similar to this, two curved lines and a bubble at the output. Instead of not, I'm placing a bubble. Okay. So y equal to a x nor b. This is a simple. Okay. A dot in a circle, an or in a circle, XOR. Okay. And they are mutually complement. So four entries again A, X nor B. Okay. Four combination 0, 0, 0, 1, 1, 0, 1, 1. Right. Right, just a complement of my XOR. So 1 0 1 1 0 was XOR. So my XNOR will be 1 double 0 1. Right? How to remember XNOR? Look at the truth table. How to remember XNOR? Same inputs, it produces a logic one. Right? Same inputs, it produces a logic one. Different input, logic 0. Right? So an XNOR gate will produce an output equal to 1 if both of its inputs are same. Both of its inputs are same. Correct? Correct. What are the minterms? Very simple. Minterms are 0, 0 corresponding to decimal 0, 1, 1 corresponding to decimal 3. So 0, comma 3. Pi terms are 1 and 2. Right? Very good. So these are exchanged. Look at this. Sigma 1, 2 become pi 1, 2. Pi 0, 3 became sigma 0, 3. Right? And what is the expression of my XNOR? Look at truth table. It should return a logic 1 corresponding to 0, 0 and a 1, 1. How to write 0, 0 minterm? A bar dot with B bar. How to write 1, 1 minterm? Product of A and B, right? A dot B. So this is the expression corresponding to A X nor B. A X nor B. Right? So minterms are 0, 3, 1, 2. Max terms. This is clear up to this. Any queries, any doubts? Very good. Very easy to identify min and max terms. XOR and XNOR both is having equal number of min and max terms. Dual gate of XOR is what? XNOR. Dual of OR is AND. Dual of NOR gate is NAND gate. Dual of XOR is XNOR. And the reverse is also true. Dual of XNOR is XOR. Dual of NOR is NAND. Dual of AND is OR. Okay. That also you can, that kind of questions also can be expected in the examination. And actually I forgot one more gate. That is my NOT gate. Okay. NOT gate. Right. This is a symbol of NOT gate. Okay. One input, one output. What is the property of a NOT gate? Related by if input is 0, output will be 1. Input is 1, output will be 0. So complement of input is nothing but output, correct? So y equal to complement of input x, correct? Correct? Right. Let us complete this also, not gate, right? Y equal to x complement. And quickly tell me what are the max terms of my not gate? Max terms and min terms. Max and min. Quickly answers. Max terms are, min terms are, what are the min terms? Right, very good. Chetana answered min term equal to 0, max term equal to 1. Very good. So we have two inputs x, sorry, we have one input x and output 0, sorry, output y. If x equal to 0, output will be 1. X equal to 1, output will be 0, right? So function f at the output is 1 if x equal to 0. So only one variable system, 2 power 1 is nothing but 2. So two min terms are possible, or two max terms are also possible, maximum numbers, right? So the function is equal to 1 corresponding to this combination. What is the decimal equivalent of this combination? 0. So sigma of 0, right? Function is 0 corresponding to this combination. What is the decimal equivalent of that? This is nothing but 1. That is decimal equivalent is 1. So pi of 1. So only one min term and one max term for NOT gate. What is a dual gate of NOT gate? That also tricky question. What is a dual gate of NOT gate? What is the dual gate of NOT gate? NOT gate is expressed as y equal to x complement. What is the dual expression of this? What is it's not buffer. That is wrong. That is wrong. How to take the dual of this expression? Look at this expression. How to take the dual? Y equal x bar is the expression corresponding to NOT gate. What is the dual expression of this? Y, will write it as y itself. Not change for equality. Not change for variable. Not change for complement. So y equal to x, it's x complement itself. So dual gate of a NOT gate is nothing but NOT gate itself. Okay, NOT gate itself. Right. Dual gate of NOT gate is not itself. Right. Very good. Right. Okay. That's all about today's class. We'll have few problems to discuss, 20-30 minutes, that we'll take up in the next class. Okay. I was a little bit slow in the initial 1 hour, so we could not get time to solve problems much. Okay, no problem. We'll make it in the next class. Okay, so let us wind up. Okay, thank you all. Thank you for your patience. Thank you for listening the class. Okay, we'll meet next time. Bye bye. And one was asking doubt. I will go to that question. Okay, you are there. Who was asking the doubt? Was asking the doubt about the last problem. So others can leave, no issues. If that question is there, I will go for that. This one he was asked. Okay, who
Sir,
was that?
sir,
Right.
DC.
All right, you are there. No, right. So
Yes,
I
sir.
should
Yes, sir.
explain this problem once again, right?
Yes, sir.
Okay, no problem. You just understand the question properly first. You are given with a Boolean expression, okay, x plus y z, okay, and you are asked to identify the number of min terms, okay, number of min terms you should identify, and you please note that it is a three variable system, three variable system, right? Three variable system. Three variable system implies how many combinations are possible? 2 power 3. Base of binary is 2. 2 power number of variables. Number of variables is 3 here. So 2 power 3 is equal to 8 combinations are possible. Okay. Those 8 combinations are written here. Correct. And each combination will have a min as well as max terms. Okay. So to identify max terms, sorry, min terms, it is asked to identify the min terms. Okay. Number of min terms. To identify the min terms, you should identify those combinations at which the function f equal to 1. Is that clear? Min terms
Okay, sir.
implies those combinations at which function f equal to 1. Correct? And this is the expression of the function. Okay. And we have two terms, x and y dot z, x plus y dot z. Okay. So f will be having a value equal to 1, either x equal to 1 or yz equal to 1, or both x as well as yz equal to 1. Okay, right? So we should consider cases individually. Let us take x case first. X equal to 1. X equal to 1 corresponding to last four minterms, right? 100, 101, in which x equal to 1, then 110, then 111, correct? So the last four minterms x equal to 1 implies the function will be equal to 1 without any doubt. Is that clear?
Yes, sir.
Correct. So what are the min terms corresponding to x equal to 1? Min terms are, look at this, 100. Min term is nothing but 4. 101, that's decimal equivalent is 5. Okay. 110, decimal equivalent is 6. 111, decimal equivalent is 7. So I have 4, 5, 6, 7. My min terms corresponding to what? X equal to 1 condition. Okay. One term we have completed. The other term is y dot z. Okay. YZ will return, the product YZ will return a logic 1 if and only if both Y and Z are equal to 1. Correct? And both Y and Z are equal to 1 here in the fourth case and here in the last case. Last case is min term 7 that we have already covered. You need not cover it again. But the condition 011 is not yet covered. Its decimal equivalent is 3. So I have min term 3 here. So total min term I should count 1, 2, 3, 4, 5, and that is my answer. Is that clear?
Yes, sir. Understood, sir.
Okay, thank you very much. Thank you
Thank
for
you.
your patience. Okay,
Yes, sir. Thank you.
shall I wind up? Any other queries?
No, sir.
Right. Nothing is there. We'll wind up. We'll meet in the next class. Thank you all. Bye bye.